All right. It is 1 p.m. Central. Um, so let's get started. Welcome, everyone. Thank you so much again for registering and attending today. I'm Layla Taha, President of the National Flood Association, or NFA. For those who may not be familiar with the NFA, we are a national nonprofit trade association that works to advance the common interests of the flood risk management community. Our membership is comprised of a diverse group of flood stakeholders representing insurance, lending, flood mapping and data, claims, and other segments of the market with a vested interest in flood-related topics. The NFA has been working to develop programs to offer more educational content to the broader industry beyond our annual in-person conference. Today's webinar is just one part of that effort, and we're looking to build an ongoing series of webinars from here. We are so pleased to offer today's session, Viewing Extreme Weather Events Through a Deep History Lens, a perspective on data-driven risk analysis. And I want to thank Dr. Hurricane Hal Needham for taking the time to speak with us today, as well as thank NFA member CNC Catastrophe and National Claims for introducing us to Dr. Hal. Before we begin, I want to encourage you all to enter any questions you have in the chat, and we will be monitoring them as we move into the Q&A portion of this session following Dr. Hal's presentation. Also, for your reference, you'll find Dr. Hal's professional biography in the speaker section of this event app, and you will find more information about the National Flood Association in this app under Documents. We plan to make the recording of the session available, and we'll let you know via email where you will be able to access it. So, it is my honor to introduce Dr. Hurricane Hal Needham, who is an extreme weather and disaster scientist with more than 15 years experience conducting data-driven risk analysis for disaster-prone communities. Dr. Hal is an international expert on coastal flooding and directs the USurge project, which provides the first comprehensive coastal flood data for the United States, Australia, the Philippines, Bangladesh, and India. He is lead scientist for flood information systems, where he develops address-based flood risk tools. Dr. Hal also hosts the GeoTrack podcast, ranked by FeedSpot as the #1 podcast on natural disasters. And you'll find a link to this podcast in Hal's bio in the speaker section of this app, so please check it out. So without further ado, Dr. Hal, welcome. We'll turn this over to you.
Layla, thank you so much for the warm introduction. I'm so excited to be here today. And wow, what an audience we have. I'm just in the process of sharing my screen, but really excited to talk about data-driven flood risk analysis. And I think we're really going to have a fun time today while we do that. So here we are. I'm just going to get into my screen share and we should be ready to go. Well, I want to start off today by talking about a story from a few years back with Hurricane Ida in 2021. I was on the ground just west of New Orleans in a place called Laplace, Louisiana. Y'all, even in the days after Hurricane Ida, it looked like a Hollywood movie set about disasters. I couldn't believe what I was seeing. I came across this family who rode out the storm in their home. You can see the ladder pulled down in their garage. When 30 inches of floodwater came rushing into their homes, they thought they were going to drown. They went up the ladder to their crawl space to take refuge in their attic. Now, that wouldn't be a problem if the winds weren't so fierce, but there were hurricane force winds in this neighborhood. This is a picture of one of their neighbors' homes. The roof is gone. You would not want to take refuge from this storm in the attic underneath your roof, but they saw no other option. They were afraid that they were going to drown if they stayed on the ground floor. When I asked them why they didn't evacuate and why they decided to ride out this storm, I was shocked by the answer. We didn't think we were at risk. We're not in FEMA's flood zone. I couldn't believe that. I'm familiar with the flood history for that area. Their area is shown here in the red star. Laplace is not far off Lake Pontchartrain. This is a map of the 1915 hurricane. Everything in gray was flooded by saltwater in 1915. You can see it produced a 13-foot storm surge in their area right off Lake Pontchartrain in 1915. In Hurricane Betsy in 1965, the storm surge was 13.1 feet. So they had two 13-foot surges. This home also would have flooded in 2012 and in 2021. I couldn't believe they're not in the flood zone because this house would have flooded 4 times since 1900 or about once every 30 years. How is it possible that a house like this is not considered in the 100-year floodplain when it would have flooded so many times in history? Well, thanks y'all for tuning in today. My name is Dr. Hurricane Hal Needham. Today's presentation is called Viewing Extreme Weather Events Through a Deep History Lens. We'll talk about cases like this Laplace case and a lot of others as we look back in history to get a better perspective on our data-driven flood risk analysis. What we'll be talking about today is knowing our local extreme weather history, taking a look around the neighborhood, how is climate change shifting data-driven baselines, a perspective on data-driven analysis, and looking at affiliated projects as well. So part one, knowing our local extreme weather history. Most people seem on board with this. And when you start talking to most people, they get excited when they mention historic storms in their community. This photograph is actually from the Great Miami Hurricane of 1926, where the salt water was up to the top of the palm trees. Could you imagine if that happened today? There'd be hundreds of billions of dollars of damage if the Great Miami Hurricane of 1926 repeated itself. So when we talk to people about long-term weather history in their area, they'll often say something like, "Oh, I've lived here for 50 years. I know all about the weather in my area." And let's take South Florida for an example. This is a map of all the major Cat 3 or higher hurricane landfalls over the past 50 years. You can see there are 6 storms in 50 years, or one major hurricane about every 8 years. So a lot of people start thinking that that's about the long-term baseline. Incidentally, if you look at this map, the first 30 years in this period, from 1973 to 2003, there was only one line, the red one, Hurricane Andrew from 1992. Andrew was a vicious, catastrophic storm that mostly impacted Miami and areas south. It was very strong, but it was very compact. Those first 30 years of this record, there's only one line on this map, and that's Hurricane Andrew. But even if we expand out to include the first 20 years or so of the 2000s, we're still seeing a total of 6 major hurricanes in 50 years. For a lot of people, they just assume that's the normal climate. And imagine if you moved here in the 70s, besides Hurricane Andrew, the 70s, 80s, and 90s, there were no major hurricanes. You may have started thinking it's normal not to have major hurricanes in South Florida. And you have some idea of the baseline based on the last 50 years. But what if we go back deeper than that, what I call a deep history lens? What if we look at the 50 years before this? Instead of 6 major hurricanes, we see 12. That's right, the 20s, the 40s, the 50s, very hyperactive periods in South Florida. In fact, if you look at this deeper history, you start to get the idea that major hurricane strikes are a normal part of the climate in South Florida. That's a very different picture than, say, if you were just there in the 70s, 80s, and 90s. I really love these deep weather histories. They give us context and a lot of perspective on risk. This is talking about hurricane landfalls, but related to hurricanes, we have storm surge, the wall of salt water that comes on the coast when a hurricane hits. I've been doing a lot of work with storm surge over the past 15 years. In fact, I run USurge, the US Storm Surge database. I've gotten high water marks from tide gauges. They're in the top left, tide gauges since 1904. National Hurricane Center report since 1958. U.S. Army Corps maps in the top right. We have those maps going back to the 1880s. What about historic pictures like the one I showed you of the Great Miami Hurricane of 1926? We have hundreds or really thousands of high water marks in different communities. And then newspapers. Just in the first 2 years of this work that I've done, from 2008 to 2010, I read over 3,000 pages of historic newspaper to start to develop these flood histories for coastal communities. What I found is really interesting. I now have comprehensive flood data sets for communities where I go back usually to at least 1880. This is a flood history for Pensacola, Florida from 1880 on, actually 1890 on. And we can see here high water marks from 55 hurricanes and tropical storms in Pensacola since the late 1800s. You can also see sea level is rising over time as well. But look at this. When you look at this, you see 52 of these are low to moderate floods, but 3 of them are much higher. The unnamed hurricane of 1906, the Great Miami Hurricane of 1926, and Hurricane Ivan in 2004. When I ask people, if you had to build in Pensacola and you wanted to avoid getting flooded, how high would you elevate your building? Most people say, well, probably around 11 feet, right? We can see 3 of these events were really between like 9 and 10 feet. probably 11 feet would be a good place to start building. So I was surprised when I dug into this and looked at the FEMA guidance. The base flood elevation, or the approximation of FEMA's 100-year flood, is 7 feet in downtown Pensacola when I did this analysis several years back. That's very shocking. Why in the world would you have people building to 7 feet when there have been 3 floods in excess of 9 feet? But again, if we just look back, say 50 or 60 years, history might look something like this. And so all of a sudden, if we're just looking from 1960 to present, we might say, well, a 7-foot base flood elevation, maybe that's reasonable. I mean, that's only been exceeded one time in the past 60 years by Hurricane Ivan. Ivan might have been a million-year storm. It was such an outlier. We've never seen anything like Ivan before. Maybe a 7-foot BFE is appropriate when we look at the past 60 years. But again, when we go back deeper into time, we see there's not one Ivan, there are 3 Ivans, because actually when you consider sea level rise there, Ivan had a little push from sea level rise. All 3 of those big events there pushed between 9 and 10 feet of salt water. So there's not one Ivan, there are 3. All of a sudden, Ivan's not looking like a million-year storm anymore, is it? Ivan's looking more like a 40-year storm, well above the 100-year flood line or the base flood elevation. So I'm going to give you a little bit of a tour here going around. Let's look at Corpus Christi, Texas, kind of on the central Texas coast there. And we see these are high water marks in Corpus Christi since around 1900. And look at this. We see this cluster of 4 pretty large storm surges, generally between 7 and 10 feet from 1960 through 1980. We see 4 of those events. But imagine if my friend went down there and built a house at 7 feet in 1981. My friend builds a house in Corpus Christi, 7 feet elevation in 1981. He may tell me, hey, I've been here 42 years. I've never flooded. He may even tell people you don't need flood insurance because I've been here 42 years and I've never had a flood. Look at how interesting, and we see a lot of clustering in the flood records. And keep in mind, a 100-year flood doesn't come every 100 years. A 25-year flood doesn't come every 25 years. These things often cluster, and we see that when we look back in the records. Another interesting case of clustering is looking at hurricanes and tropical storms passing within 75 nautical miles of Hilton Head, South Carolina. This is an archive that I found in the Charleston Library. Look at this, 8 hurricane passes in 11 years. Now, these didn't all make landfall, but they were in the neighborhood. 8 hurricanes in 11 years. And then in the following 48 years, 0. I mean, amazing clustering. If you were in Georgia and the southern part of South Carolina in the 1800s, you'd have to say this is probably the most vulnerable place on the planet to hurricanes. And then you get into the first 5 decades of the 1900s and you'd say, oh, hurricanes never hit southern South Carolina and Georgia. Again, there's strong clustering when we look back at the historic data. Well, there's a game that you can play at a party. You might try it this weekend. It's a lot of fun. What you do is you take a quarter and you take 10 people and you put 10 people in a room. One of the people leaves the room. So now you have 9 people in a room. You give them each a sheet of paper and you ask them to make up a sequence of 50 coin flips. Make believe you flipped a coin 50 times and you just make this up. Heads, tails, heads, heads, tails. You get 9 people to make up a sequence of flipping a coin. And then you actually flip a real coin 50 times and you write down that sequence on the 10th sheet of paper. Now, the person who left the room comes back in. There are 10 sheets of paper in front of them. 9 of them are made up. 1 of them is real. And there's a trick to find out which one is real. What is that trick? Since we're not in a live audience today, I won't wait for your response, but here's the trick. The way we think of this is heads, tails, right? Maybe 2 heads in a row, 2 tails in a row. The real sequence looks more like this. Heads, tails, heads, heads, tails, 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 tails. People never think you're going to get 5, 6, 7 in a row, but that's what happens in reality. You see strong clustering in real life. And again, this is just flipping a coin. This is randomness. But again, people think it's going to go back and forth very frequently. A lot of times you get these long runs that surprise people. It happens with coin flips. It happens with hurricane and flood climatology as well. Let's look back at Pensacola, Florida here. So when we take these high water marks from all these storms, this is one of my favorite parts of the presentation, y'all. We take these data, these high water marks from 55 hurricanes and tropical storms, and we can actually build our own flood zones. We're not limited to just talk about the 100-year flood zone. We can build out what we think statistically, we run statistics on all these data. What's the 10-year flood zone? What's the 25-year flood zone, the 50-year, the 100-year, the 200-year, the 500-year? We can build as many flood zones as we want. We're not limited by just the 100-year flood zone. Look at this. Remember where I said the base flood elevation is 7 feet? That's very close to the 25-year flood, according to our data-driven analysis. So imagine this. Imagine that you move down from Chicago to the Gulf Coast. You love the warm weather along the Florida Gulf Coast. You don't know anything about hurricanes. You've never lived here before. You trust the system, and the system tells you the 100-year flood level is 7 feet. So you build to 7.1 feet. You think you've built to the 100-year flood level. Our data-driven deep history lens says you haven't built to the 100-year flood level. You've built to the 25-year flood level. And keep in mind, if you've built to the 100-year flood level, you have a 1% chance of flooding annually. Look at this, where it says 25 years there, 7.1 feet. We've also calculated your risk of flooding in a 30-year mortgage. You've built to what FEMA calls it, the 100-year flood level. It's actually, we think, the 25-year flood level, and your chance of flooding in a 30-year mortgage is 76%. You've done everything you're supposed to do. You've built to compliance. You're above the 100-year flood level. And our analysis suggests you have a 76% chance of flooding in a 30-year mortgage. We can get an idea why so many people get blindsided, are caught off guard, or just think, wow, we're having 100-year floods every few years because of climate change. Climate change does play a role, but if we really grossly underestimate the extreme levels to start with, we can expect to see 100-year floods all the time because we've grossly underestimated what the 100-year flood level is. So this type of statistical analysis, again, I'm not modeling anything, nothing theoretical here. This is based on observed data for 140 plus years. I've done that for 26 Gulf Coast communities. And again, I don't have time to talk about each one, but these bars here, the top of the highest bar is the 500-year flood level, then 200, 150, 25, and 10. This analysis is several years old. It's before Hurricane Ian and some of these West Coast Florida storms, but you get the idea. The red dots here are actual real-world observations that make up those statistics. And we can see a pattern here. One of the patterns is that flood risk really changes quite a bit depending where you are. Look at cities 16 and 17 there on the Mississippi coast. That's probably the most vulnerable area to coastal flooding in the Western Hemisphere. There are a lot of physical processes why some of these areas are so much higher than others. Places like Mississippi, very shallow water, and you're at a right angle there with the Mississippi River Delta in Louisiana. The water gets trapped there by extreme eastern Louisiana and Mississippi. Some of these areas, there are real physical reasons why their risk is higher. But then you go over to the Texas coast, you can see that, for example, city number 3 is higher than the others. They are on a bay. Bays, inlets, and harbors tend to increase your flood risk. That said, city number 3 had the unfortunate history of getting a direct hit from Hurricane Carla in 1961. It was the highest storm surge on record in the state of Texas. So some of this also is a bit of randomness. Some cities are less fortunate than others, even if you look back 100 years. And so that brings us to part 2 of this presentation, looking around the neighborhood. And what I mean by this, imagine that there's a man that lives in a city and he's heard a lot of his neighbors have been robbed. So he looks out and he might say, hey, I've never been robbed. I'm just really lucky and the robbers will never come to me. Or he might say, there's maybe a lot of randomness with this and I need to look to my right and I need to look to my left and consider if my neighbors are getting robbed, maybe my risk is higher than I previously thought, even though I haven't been hit. And so this concept of randomness, of looking around the neighborhood, deep history is important, but it's also important to realize that there's randomness in these data. So imagine a die. You roll a die 6 times. What will you see? Chances are you will not roll each number one time. You may start to see what look like trends and patterns. Maybe you say, I always roll low numbers. I get a lot of 1s and 2s, but I never seem to roll 5s and 6s. If you roll that enough, you're going to see every side of the die has an equal chance of being hit. But if you just roll it maybe a few dozen times even, you're going to see what look like patterns that aren't really there. There's a lot of randomness. I really like Nassim Taleb's book, Fooled by Randomness. He talks about how people on a limited statistical sample all kinds of conclusions and see patterns that aren't really there. And so let's talk about Hurricane Ian. When Hurricane Ian hit last year, it was so catastrophic. I still have a heavy heart from this storm. It hit there by Fort Myers and Cape Coral, Florida. A lot of people were saying, hey, a 14-foot storm surge on the west coast of Florida, we never could have expected this. The only explanation is climate change. There's never been anything like this. Well, this was an exceptional hit for Fort Myers, but look to the right and the left. When we are looking at the coast and we go down to, say we go to the south, look at Hurricane Irma from 2017. It missed a direct hit on Fort Myers, but south of Fort Myers, down by the Everglades, there was over 9 feet of saltwater inundation above ground level in parts of the Florida coast. It takes about a 12 to 14-foot storm surge to get that much inundation. So there was a big hit. People say Hurricane Irma didn't have a surge. It did. It just was not in a populated area. Well, what about to the north? People say, well, Tampa never gets hit by a hurricane. Well, it seems like that in recent decades. But when I was in Florida last year for Ian, I researched the Tampa hurricane history, and I found some interesting things on the Great Tampa Hurricane of 1848. Look at this. This is September 1848. Tampa was a new community. It had an army fort called Fort Brooke. At 11 o'clock a.m., the barometric pressure stood at 30.122. 3 hours later, it bottomed out at 28.181. This is a book by Cantor Brown talking about observations from the 1848 hurricane. By then, the water stood 15 feet above mean low water mark. A 15-foot storm tide above mean low tide in Tampa in 1848. I realize it's a long time ago, pre-Civil War. Florida was only a state for 3 years, but look at the accuracy, the barometric pressure recorded to 3 decimal places. The salt water recorded above the tide, above the low tide mark. That's what we call a tidal datum. It shows it's a very accurate observation. Basically, a 15-foot storm surge in Tampa Bay. And the month after this, there was a 10-foot storm surge in Tampa Bay, back-to-back months. Can you imagine if we repeated 1848 today? We'd have hundreds of billions of dollars in losses. So that's the importance of looking to the right and the left. And sometimes your city hasn't been hit, but cities near you have been, and that may indicate that your risk is higher than you realize. Part 3, how is climate change shifting these data-driven baselines? So we're going to talk for tropical weather, and for coastal flooding, we're going to talk about sea level rise, rapid intensification of hurricanes, slower moving hurricanes and tropical storms. Increased moisture means more rain, but not necessarily more named storms. People tend to think everything's getting worse. The models do not suggest we're necessarily going to see more named storms, but a change in the characteristics of the storms that are out there. Let's talk about sea level rise. I took this picture where I live in Galveston, Texas. We're starting to see sunny day flooding in places like coastal Texas, coastal Florida, where salt water is pushing in even without a drop of rain. That's happening because the oceans are getting warmer. That's called thermal expansion. Warm water takes up more room than cold water. Also, we see a lot of land-based ice melting. We can see this in these photographs of glaciers in Alaska, the difference between 1941 and 2004. When that land-based ice melts, it has to go somewhere. It goes in the oceans, and we have sea level rise. Also, in places like South Louisiana and the upper Texas coast, we're seeing a lot of subsidence or our ground sinking. That's a big problem, y'all. This is a photograph I took in my town. On that top stair, this is in Galveston's East End Historic District. That top stair is a high water mark from Hurricane Ike 15 years ago. That house stayed dry during Ike. If Ike hit again today, that house is flooded. Right now, we're getting about 4 inches of relative sea level rise every 12 years. So again, same storm hits today. That house has damaged hardwood floors. It's a historic house from the 1890s. Damaged hardwood floors from a storm surge that did not flood it in 2008. Today it would because of sea level rise and subsidence. This one really keeps me up at night, y'all. This is one of my biggest concerns, especially for the Gulf Coast, rapid intensification of hurricanes. Look at this. Over the past 7 years, we've had 6 hurricanes rapidly intensify right before landfall. The one in the top right, I was just doing field work in that storm about 6 weeks ago. That was Hurricane Idalia. But all of these ramped up at least 40 miles an hour in the last day before landfall, often going from like a Cat 1 to a Cat 4 in less than 24 hours before landfall. This is a big concern, y'all. And look at this. This has happened 11 times since 1950. 11 times since 1950 and 6 times in the past 7 years. Again, is it random? Is it just you're rolling the die and you keep getting a 5? I don't think so, because I see a physical process tied in with it. We do not have air temperature record, or we don't have water temperature records going back more than 100 years or anything like that. But where I live in Galveston, we have the longest continuous weather records west of the Mississippi River. We have weather records here, continuous, where I live, going back to 1871. I looked at this plot of the overnight temperatures in Galveston. And the reason I chose Galveston, we have a long weather record. And in the summer, we get a continuous onshore wind blowing from water to land. And I plotted this out, the number of hot nights per year. We never had a hot night until 1927. Then we started getting nights where the low temperature reached 84. In the mid 90s, we started getting nights where the low temperature hit 85. Look in the past several years, we see the introduction of 86-degree nights and 87-degree nights. I think this is directly correlated with the incredibly warm water temperatures in the Gulf of Mexico. Warm water gives you a lot more fuel for rapid intensification. Again, this is one of my big concerns with climate change, of these rapid intensifying hurricanes that are striking our coast. And it's a big problem for things like evacuation. And also, obviously the impacts on the built environment. Number 2, hurricanes stalling out as they make landfall. I did a piece with PBS NewsHour called "How a Warming World May Have Caused Hurricane Florence to Stall" from the Carolinas in 2018. The models suggest that we're going to see slower moving storms. The whole reason we have storms is to move heat and energy from the tropics to the poles. We know the Arctic and the polar areas are warming faster than the tropics. This reduces the gradient, or the difference between the Arctic and the tropics. In theory, the models suggest we should see slower moving storms, and we've seen a lot of those in recent years. A slow moving hurricane or tropical storm can dump a lot more rain than one that's moving quickly. Also, warmer ocean means more rain. So if you warm up the ocean water by 1 degree Celsius or 1.8 Fahrenheit, you get 7% more moisture in the atmosphere. And we know these storms converge or collect this moisture. So what is 1 degree Celsius of ocean warming mean as far as the more rain in tropical systems? We don't know exactly. I took these data from Scientific American blog, but perhaps 10 to 15% more rain for each degree Celsius of ocean warming. It's a big concern. This is a photograph I took from Hurricane Harvey here in Florida, in Texas, but a huge concern moving forward of seeing more rain from these storms. So again, I do a lot with history. I create these baselines, but you have to build a buffer, and you have to consider how climate change may shift some of these baselines. Well, part 4, what about perspectives and pushback on data-driven analysis? I hear a lot of different comments on the work I'm doing. One of them is, hey, the models already rely on historical data. How is your work actually doing anything new or contributing to science? And my response to that would be, the models do use observed data to validate some of their large set of synthetic storms. But however, the core of their analysis relies on theoretical modeling. So what the models do, they might take a place like Fort Myers or Tampa or New Orleans, and they might run 10,000 synthetic hurricanes, different strengths, different forward speeds, coming from different angles. And they're doing all that to really model what's the potential of wind and flood risk in these places. We absolutely need this type of modeling, because there's always a hurricane out there that can come from an angle or have characteristics we haven't seen. However, I wanted to point out, although the models do use some data, especially in the recent decades, to validate some of their model runs, the core of their analysis relies on theoretical modeling. When I showed you those statistical high water marks and the map for Pensacola, that's not based on anything theoretical. That's based on those 55 high water marks from historic storms. And again, I've done that for 26 Gulf Coast communities. So what I'm doing is 100% based on observed data and statistical analysis. Perspective number 2, you're looking backwards. What we really need to do is look forward and consider a changing climate. I hear people say a lot of times, my work, our work just building historical data sets and running statistics, that's great and all, but we need to look to the future, not to the past. My response to that would be, what we're doing here by building out your flood history is we're building a baseline based on observed reality. This is vital because most communities are not prepared for their past. Now, you might say, hang on, did I mess up that slide? Surely I meant to say they're not prepared for their future. No, I meant they're not prepared for their past. If most communities said, we can't build below previous flood lines, they would be incredibly better prepared for future flooding than they are. My point is, when you look back at flood history, a lot of communities are building new construction in places that would have already flooded 3 or 4 times in the past 140 years. So my point is, they're not even prepared for the past, let alone the future. So our approach here is to build a data-driven baseline. Look at regional neighborhood. Again, you have to look to the right and left. Some communities are going to be more lucky than others, but if I'm thinking about places like Destin, Florida. They've had a bunch of hurricanes to the south, a bunch of hurricanes to the west. I've talked to people there say, we never get hurricanes in certain parts of the coastline. Again, you're rolling the dice, and some of that is just good luck. That'll eventually run out. And number 3, we need to consider climate change and build buffers. Again, just looking at the past and building those baselines, we're not saying that things are not changing. We need to build buffers and consider climate change accordingly. Our ultimate goal, to align our analysis with reality as much as possible. Before I close out this presentation, I want to give you one example, a real life example. All of us drive in traffic every day, so you may find this example to be relevant. I'm going to take a quick sip of water, and then I'm going to tell you a story before we wrap up the presentation. So a couple of years ago, I had to rent a car for the weekend. And so I had to drive where I live in Galveston, Texas, up to Houston Hobby Airport to Enterprise Rental Car. And that usually takes about 45 to 50 minutes. I pulled up the smartphone map. It told me it should take 47 minutes. I thought that's about right. So I got in my car, I hopped on I-45 North, and the trip took me about 47, 48 minutes, just like my phone said. I drove up there on a Friday afternoon. It looked a lot like this. I rented my car. I brought it back to my community. I spent the weekend with my friends here on the island of Galveston. And then on Sunday evening, it was time to return that car. And so I want to ask you a question. I've done this drive many times from Galveston up to Houston Hobby Airport. Usually takes about 45 to 50 minutes. On Sunday afternoon, I pulled it up. My phone said, again, it's going to take about 47 minutes. And again, I've done this drive many times. It's very consistent. My phone saying 47 minutes. On Sunday afternoon, when it was time for me to return the car, how much time do you think I gave myself? Again, since we're not in a live audience, I'll just give you the answer. I gave myself about 47 minutes, maybe an extra 5 to fill up with gas. But I thought it's going to be a lot like Friday, right? So late Sunday afternoon, I get on the road, and this is what I see in Galveston. Gridlock. I think, oh no, I got to return this rental car. I don't have a big buffer. There must be an accident up ahead. Well, as I'm inching ahead in traffic in this gridlock, I'm seeing there's no accident. Well, maybe construction. Are they doing construction on the weekend? No construction. About 15 minutes in, I realized I just got blindsided by a pattern I didn't foresee. And this pattern has to do with, I live on a tropical island with a beach. The 4th largest city in the country is an hour away. Every weekend, we typically get tens of thousands of tourists that come here. They come on Friday, they come on Saturday, they come on Sunday. Most of them want to go home late Sunday afternoon. This is tourist traffic going from Galveston to Houston. It's a pattern. It's not an accident. It's not construction. What happened is the model in my brain that told me that theorized how the world works, my smartphone map, which theorized how the world works, they both were wrong, and I got blindsided by reality, by observed reality. And I've noticed, now I know there's a pattern. If I have to go from Galveston to Houston on a late Sunday afternoon, I'm going to give myself a lot more time in the future. This is what we're doing with data-driven flood risk analysis. Models are incredibly important. We use them all the time. They're super important. But we also need to verify them with real-world data. If I were to drive to Cincinnati, the first thing I would do is pull up my smartphone and see how long it takes. I'm not familiar with that route. I need a model to help me and to say roughly how long it's going to take. But imagine if a friend of mine was a truck driver and he's driven that route from Houston to Cincinnati 263 times. How ridiculous would it be if I didn't say, hey, how long does that usually take? right? He's done this 263 times. He may say, well, your smartphone map's going to take you through Nashville, but I would avoid it because of construction or because of gridlock, right? So if you've been on the ground and you've observed reality, you can really help improve a forecast or a prediction or a model. And that's my point here with data driven stuff. It's not a replacement of the models, but it's a way to keep from being blindsided and to verify our models with real world with observed real world observations, if you will. So that's I hope I said that clearly. My point is we need models and we need data driven, and hopefully they can work together to keep us from being blindsided in the future. Hey, as I'm wrapping up here, a couple affiliated projects. These are really funded by our parent company, CNC Catastrophe and National Claims. Check out the GeoTrek podcast and the GeoTrek project. We're doing a lot of social media clips. We're going into disasters. We're doing a podcast on all kinds of disasters, not just floods. We've talked about building better for severe weather, for blizzards. We talk about drought. You name it, we're talking about it. You can find it on Spotify, Apple Podcasts, wherever you listen to podcasts. We're usually ranked as either the number one or number two podcast in the topic of natural disasters. Next week, we're going to do a review of Ian a year later and talk to some experts in Southwest Florida there to see what's happened with the Ian recovery after a year. Finally, too, check out flood information systems. We're launching address-based flood forecasting in addition to these historical data sets and these statistical analysis of our data-driven flood levels. We're actually superimposing tens of thousands of building elevations for communities onto these maps. We're building a massive map for Galveston, Texas right now that should have the building elevations for more than 20,000 buildings. We can look at a building and say that building should flood on average every 83 years based on 140 years of history. We can also take a building and tell you if it's flooded before. My friends in real estate love this. We can take any building and say, hey, that building would have flooded 3 times in the past 120 years, things like that. Again, we're superimposing thousands and thousands of building elevations on top of our historic flood data and our data-driven flood risk analysis. Well, y'all, thank you so much for your attention this afternoon. Again, I'm Hal Needham. A lot of people call me Hurricane Hal. I'm an extreme weather and disaster scientist. I'm based in Galveston. There's my email. There's actually my personal phone number. Maybe I need better boundaries with this stuff. Just give me a call, give me a text. You can call me in the middle of the night. I don't care. I just really love engaging with folks about this stuff. It's exciting. People love this. They love building out these histories for their communities because it really helps align what they're doing with reality and hopefully helps better protect them moving into the future. I hope we have a little time for some questions. Again, I appreciate your attention today, and thank you so much for staying tuned on the broadcast.
Thank you so much, Hal. That was great. I'm laughing at your needing better boundaries potentially, but clearly you're so passionate about this. It comes through so clearly, in your presentation. Really appreciate the perspective and all the data that you shared. It's fascinating. I see we have one question. So we want to do as much Q&A from the audience. I have a couple of my own questions, but I'm happy to defer to the audience first. I see that Dawn Brown has a question here, and I'm putting that on screen just to make it a little bit easier. But how has FEMA taken these statistical forward-thinking metrics into consideration for updating their firm's flood insurance rate maps?
Yeah, it's a great question. I mean, again, I think we need modeling, but we also need to confirm these with real world observations. I don't know specifically how FEMA has done it. I've talked to a lot of communities that really want to see their flood history because sometimes they can build in what we call freeboard. So FEMA might say their base flood elevation's 9 feet, and they're saying, based on our history, we want to build in a 2 or 3 foot buffer. So I'm a little more familiar with communities that have come along and said, we really want to know our history because we may want to build in a buffer. As far as FEMA, I would love to see them verifying the models with real world data. I don't know specifically if they have plans to do that or not.
Right, right. And I know that the flood insurance rate maps, are the data is determined based on certain science that they have in place, and then they have their cooperating technical partners who then go out and they performance studies and all of that. So, I mean, I would think that that would require some revamp of their, their methodology and their standards and things like that. But that being said, I mean, it's definitely valuable data. So certainly, something for them to consider for sure. And I was really, so there are a couple things, taking some notes. I don't see any more questions from the audience yet, but please, you all feel free to enter them, and we're just keeping our eye on that. But I like this, building a baseline based on observed reality. I think that that's really, such an interesting way to position that. And a lot of your examples are just, really, resonated. One of the things that I was wondering, we've been hearing a lot about flood models and AI and all kinds of new technologies, and not that those aren't based on some historical data, but how can we what are your thoughts on um, how this data can augment that data, or perhaps any strengths or weaknesses with that kind of data or that sort of methodology that perhaps this data could help to improve?
I see these data as really low hanging fruit, a great place to start. If we know a community has flooded 4 times before, I feel like that needs to be in some kind of flood zone or communicate that this has enhanced flood risk. That said, where I see AI and some of this advanced supercomputing, I'm kind of doing this at a community level. Like I get the high watermarks for the whole community, but we know, you probably know from your neighborhood, some streets flood more than others. Maybe they have worse drainage. I think at a very micro level, there's no way I could be that granular with my analysis. This is where maybe modeling and AI and machine learning can come in to say, okay, let's take what USurge and what flood information system said about the big picture, but then let's tweak that and localize that a little more granular with, say, like localized drainage and things like that to make it more precise. I think absolutely we could take this data-driven approach and improve it, localize it with some of these advances in modeling.
Yeah, no, that makes sense. That makes sense. So, are you all working currently with communities, or are communities using this data today in the US?
We've had a lot of communities interested. We've had grant projects where we've been funded. In fact, a recent one with Biloxi, Mississippi, where they said, we really want to know our historical data. And what we did with that project, we built out their flood history, ran statistics on it, and then we did an elevation map of about 1,200 buildings in a very strategic part of the town that the city wanted to know flood risk. And so we've had communities very interested in this, both from understanding the flood history, but then building out these building elevations as well to know, okay, if these flood levels happen, how many buildings would get inundated?
Right, right, right. And I think I recall you saying that you are still in the process of developing the data for at least most of the critical coastal communities in the US. So, where are you in the process, or what percentage of those communities do you have completed thus
Yeah, we
far?
have what I would say a pretty good, if you want to say a preliminary data set for 26 Gulf Coast communities and 20 Atlantic communities. We're if we really wanted to do this robust, more accurate thing, a community wants to build a flood wall or do some advanced analysis, we would take a little more time to zero in on that. But I would say we have at least a really good baseline analysis for 26 Gulf Coast communities and 20 Atlantic communities.
That's great. That is That's impressive. Looks like we have a question from the audience that is relevant here as well. So, if a community wants to research their flooding history, how do you recommend that they do that? And where do we find the historic information?
Yeah, that's a good question. I was asked early on, even when I built the first version of this, where did you get the data? And my response was, the data are really everywhere. So just in the first take of this database for the Gulf Coast, I used 63 different sources of data. So they're really everywhere. If a community wanted to build this out, get in touch with us. There's a good chance we've already built the data for that community. If they want to work on the local level, starting with librarians, historians, local colleges, sometimes even community colleges or just your local colleges and universities can be a good start. Historians can be a good source as well. Again, we want to take everything. It can be journal entries, newspapers, historic photographs. Sometimes you just need one historic photograph from 1923 and you say, wow, the floodwater got higher than we realized in that storm. And then you adjust your high water mark. So really you want any information you can find, historical resources. They don't have to be meteorologists, is what I'm trying to say. Historians, local library, that's a great place to start in a lot of these communities.
Great. Thank you. Thank you, Janet, for the question. One thing that I was wondering as well is you mentioned your parent company, pardon me, which is CNC Catastrophe and National Claims. They're also an NFA member. So thank you again, CNC, for putting us in touch with Dr. Hal here. But I was wondering how this data can be used in the claims process. Is it being used today? Is CNC using it? Sorry, if that's a secret sauce there. But just very interested in how the data might be used by the claims community.
You know what's really interesting? As I started with an academic background for 12 years, and then I got more on the private side and started working with CNC. I was amazed how many adjusters are out there on the ground after a flood, already documenting high water marks, taking pictures of this. All of this we ingest into
Oh,
USearch.
nice.
So we really take these. We take data from everywhere. We'll use FEMA reports, National Hurricane Center reports, Army Corps, but there's often a lot of dense data from adjusters. And what I mean is a National Hurricane Center report might say the high water mark in Cape Hatteras was 6.1 feet. But then the adjusting community, we might have 10 adjusters that were working that community that have claims for 32 houses. That can help us, I think, really start to see some more of these very localized granular patterns. In other words, okay, we know there was a 6.1 foot storm surge, but how did this play out? Were some streets inundated more than others? I think in that localized level, the work that adjusters are doing, getting all that very dense amount of data, I think that could really be used with AI and machine learning in the future to better understand these patterns.
Yeah, that's a good point. That's really interesting. Looks like we have a question from David Conrad here. Are there any other countries you're aware of that have also built out and made publicly available their deep historical flood data? Any models that happen to stand out?
Yeah, I did this for the US and then I go overboard sometimes. So I started building out the Australia data set and then India and Bangladesh. And then I was working closely when I was doing my doctoral research with Pagasa. So they're like NOAA in the Philippines. They were sharing a lot of their resources with me, and I was building out their first coastal flood database for the Philippines. And that's how I ended up doing a lot of work with PBS along the way, too. So a lot of communities and a lot of countries are very interested in this as well. Especially, I'm a little more familiar with those that get hit by hurricanes and typhoons and tropical cyclones. I know the interest is out there. Again, a lot depends on the government behind it. Like the Bureau of Meteorology in Australia does an amazing job. They have reports going back to the early 1900s. So that because of their great work, I was able to build USearch for Australia, much more efficiently than otherwise. As far as models that stand out, I would need to look into that a little bit more. Again, I'm a little more familiar with the models in the US. As far as what's going on internationally, I'm not sure specifically. I would need to look at that. But again, I think it's the similar idea that models and data can hopefully work together. The models are showing us stuff that we haven't seen before. We're always going to see a new track of a hurricane that we haven't seen in the data. So I definitely don't want to imply that all you need is data, but also I think the data can help verify the models.
Great. Thank you, David, for that question. So one other thing that I had jotted down, so you talked a lot about coastal communities and storm surge, and obviously the USurge project is very, very focused on that. But maybe once you've completed your analysis and your data collection for coastal communities in the US, that you at least feel kind of fit this model, are you going to be looking more at inland communities or anything else that's maybe outside of what your current focus is, especially because we keep hearing about, precipitation inland flooding, areas that are really getting hit hard by these storms that are maybe not hurricanes. So, is that something that you've thought about or might expand into?
Layla, I'm really glad you asked that. We're absolutely interested to build this out inland as well. I mean, I opened with a story about Hurricane Ida. That was a Louisiana storm, but it also became a Pennsylvania, New Jersey, and New York storm in the days afterwards, devastating flooding in the mid-Atlantic states. So we know a lot of these storms that may even start as tropical in the South work inland. We've seen horrific inland flooding in recent years. So we definitely want to work and partner with communities as well that are not just on the coast, but inland as well.
Right. Great. That's great. We look forward to that. So you shared your contact information. So if anyone is interested in the data or accessing it or using it, that's something that they can contact you about as well, as opposed to just maybe some general questions or just general inquiries that they might have.
Absolutely. Yeah, Layla, really want to hear from people if they're interested in the data, if they need it for any reason. They're not just available online where you can download them yet. We're in the process of still figuring out how all that works as far as accessibility. But right now, we're really taking a collaborative approach. So we love to hear from people that want to work with these data. They want to use these data. Give us a shout. Let's have some conversations and see how we can maybe work together to help these data, help your project and help it, like we said, align with reality, and just to give you a different perspective on flood risk for your community.
Great, great, great. We still have a little time for questions. I see one from Kenneth Somerset here. Go ahead and put that on screen here. Thank you. So do you work on creating the maps with elevation certificates as a community has only as a starting point?
Yeah, great question. So I think this really gets into the work we're doing with building elevation mapping. So elevation certificates are this sheet of paper from a certified surveyor who come to a house and do surveying and give you an elevation certificate to tell you the elevation of your home. In a lot of these projects that we've worked with, we've taken those elevation certificates from the community, but we realized that in most communities, most of the buildings do not have an available elevation certificate. So we've developed and innovated some other methodologies that enable us to map out the building elevation of every building in the community. Often the elevation certificates help us calibrate our technology to make sure that we're accurate. But elevation certificates are a great place to start, but we're not limited just to them. So we can usually map out most buildings in a community, even if we don't have an elevation certificate.
That's great. That's great. Hal, Kenneth is asking, and I'm sure other people are interested as well, if you would maybe reshare the slide that had all your contact information on it.
Yeah, for sure. Let me do that. I'm going to
And
pop
while
up the
you do
screen
that,
share here.
great, great, great.
Yeah, absolutely. This will just take me a second. I'll pop
Sure.
that up.
And in the meantime, we have another question, but whenever you're ready.
Oh, you can shoot that over. I'll pull up this.
Okay.
So I don't know if you can see my face, but hopefully you can see this slide here. I'll share from here.
And
So
we
that's my
can,
contact info.
okay, so sorry. Great, thank you, Hal. We'll also be sharing this information. I think that we left your contact information out of your speaker bio, but we can
Sure.
certainly add it in there. And everyone who is in here and registered will continue to have access to the materials for this session. So we'll make sure that everybody gets it as well. So one more question here that just came in from Janet. What kind of evidence of flooding do you look for, and how do we know it flooded?
Oh, that's a great question. A lot of times you get into a flooded community and the floodwater has receded by the time you get there. So you're looking for, a lot of times, ideally, if you want to know the still high water mark, a building that flooded where you actually have a water line on the inside of the building, that kind of takes away some of the wave action. And so that'll give you a pretty good still high water mark. Sometimes you can't get high water marks inside buildings. You might have watermarks on the outside. We look for things like grass lines, rafted debris, they call it. So you could actually see on the landscape sometimes a line of debris with leaves and sticks, things like that. But in general, in the built environment, usually there will be some kind of mud line or water line that's left behind. Sometimes it's different on the inside and the outside of the building. It sometimes will be a little bit higher on the outside because it was flowing fast and a little bit of wave action as well. But we're looking for any clues we can. We'll take pictures, take measurements, and again, we archive all of those data.
That's amazing. It's great. Great question.
Layla, one more thing that comes up a lot of times. People ask who uses these data. I've been amazed by the different sectors. I mean, obviously academic researchers, people doing flood modeling. We also see a lot of people in the private sector. One of the groups that really surprised me are realtors. People told me realtors are never going to use this. They just tell everyone there's no flood problem. In flood-prone communities where there's been a lot of flooding, I've been surprised by how often realtors say, no, we want to actually tell our clients how often this building would have flooded. And I've been really encouraged by a lot of realtors out there really want to know the truth. They'll tell their clients, you're interested in these 3 houses. This is the one that's never flooded before. And they're very interested in these data.
Yeah, we've definitely seen the realtors take much more of an interest. They're now incorporating flood zone information on their sites. So for listings and things like that, they're helping to disclose that information up front. They've been very, very active actually in addressing issues and finding ways to better inform home buyers. So that is really interesting. They were not on my short list, but that was great to know. It looks like we have one more question from Rodney. And while BFEs are a FEMA thing and maybe not your thing, Hal, maybe you can describe how the BFEs are mapped or determined.
Yeah, so this is really interesting. I'm glad we're talking about this. We started talking about rating, so originally there were essentially models trying to determine where's that 100-year flood line. And so historically, a home is either inside or outside the BFE. We know with risk rating 2.0, we're getting away from some of that, where we're taking each building independently. But I do know that base flood elevations and the floodplains are still used a lot for flood risk determination. So in other words, are you required to carry flood insurance or not? A lot of times that they're still using the floodplains and the flood zones to determine that. How these are developed, again, they're synthetic models that are running hypothetical storms. I do believe some of those are verified with some data, but again, it's not really a completely data-driven analysis. It's based a lot on synthetic and hypothetical science. I'm not discounting it. Again, we need the models, but I think to verify it with data, I think you're just making it so much better.
Yeah, absolutely. Thank you, Rodney. Great. See any others? I know we're getting close to the top of the hour, so that's great. So if no other questions, Hal, thank you so much. I can't tell you. I mean, I think we could probably spend many more hours on discussing the data, and especially for those of us who are just data enthusiasts in general. This is just it's fascinating. So really appreciate you taking the time to speak with everyone. Appreciate everyone for joining, and appreciate again CNC for putting us in touch. CNC is an NFA member, and just being able to share information like this and opportunities like this is just so valuable. So we thank all of you. As we close this session, I just want to remind everyone that you will continue to have access to the information in this app, and we will let you know where you can access the recording. So just give us a few days. We want to be sure that the recording is high enough quality to be able to share. So we will let you know via email when that's available. Also, I encourage you to check out NFA's 2024 annual conference, and you'll see a shameless plug there up on the screen. Our conference will be held March 24th through 26th in beautiful Scottsdale, Arizona again. The NFA has been hosting an annual conference for more than 25 years, and the event is an excellent opportunity to learn about relevant flood topics in a more intimate setting. That allows for open dialogue and networking. Our team is actively planning a very robust program for next year, which I'm already excited about. And we expect registration to open this month. So check out our website, as well as our LinkedIn page for more details in the coming weeks. And we hope to see many of you in Scottsdale next year. Thank you all for joining us again today. Thank you, Hal. Thank you, CNC. Take care.